The second part of this introductory section on node voltage analysis, I'm going to write the formal equations for solving for node voltages and do it in a matrix equation form so that it would be very easy to go ahead and implement a linear system solver by hand or doing on a computer calculator to be able to resolve those node voltages. So example 3 on the bottom of page 50, we have this situation. We have a independent current source, independent voltage source, and we have 4 resistances here. Again, with no opportunity to exploit series or parallelism, and we want to apply node voltages. In this case, we have identified 2 node voltages. Noticing that we're not going to specify the center one as a node voltage because we have a voltage source there. So the voltage at that node is exactly 10 volts. Okay. So in this case, what we'll do is, again, we're going to write KCL equations, which define the sum of outgoing currents to see if we can get a relationship between these node voltages. This is node 2, of course, and this is node 1, right? So, so we'll start off with writing the KCL equations for node 1. I'm going to do it, instead of flipping to page 51, I'm going to do it here right on the top here. So while we have this circuit diagram in front of us. So again, applying what we know about NBA, we're looking at node 1, and we should have 3 components because there's 3, we could represent 3 outgoing currents. One of them, we could say, let's suppose we went up out of node 1 over to node 2, going through the 5 ohm resistance. So in that case, what we would have in that component would be V1 minus V2 over 5. If we were representing the the current coming directly to the right, going from node 1 through the 2 ohm resistance to the voltage here. And again, we know the voltage here is 10 volts. Exactly. So in this case, we would have V1 minus 10 over the resistance. In this case is 2 ohms. Okay, so we'll just put 2. Okay, so I'm not labeling the resistance here, R1, R2. I'm just go ahead and using flat out what the ohmage is. And then here representing an outgoing current, if the independent current source is coming in, then we would subtract 1 amp out of it, and there would be one equation, okay? Similarly, we can do the same thing for the second node. So let's do KCL for node 2 and come up with a second equation, because in this equation we have 2 unknowns. That would be the infinite number of solutions, so we need another equation involving both of these node voltages. So over here, let's suppose we go down from the voltage for node 2 down to the ground, which has voltage 0. So that would be V2 minus 0 over 5, or just V2 over 5. Then let's suppose we go up and over again backwards. V2 goes back to V1. Notice that you'll get the same thing up here. It's just the signs are reversed. V2 minus V1 over 5. And then finally, we go from the to the left and go from this node voltage over to 10 volts. So we'll go plus V2 minus 10 over 10 ohms, and sum equals 0. So in terms of resolving these node voltages, you could clean this up by collecting all of the like terms for V1 and V2, find common denominators. And if you did that in this case, this first equation would turn out to be 0.7 or 7/10 V1 minus 0.2 or 2/10 times V2. And then on the other side, we could show that's going to be equal to 6. Again, you're just getting common denominators and then shifting constant terms over to the side. Okay. Right? For this other equation, simplifying it, you could show this is 0.2 V1 plus 0.5 V2, and that will have to be equal to 1, okay? Right? And you can see that because you've got 10 over 10 there, that's going to give you the 1 there, right? So now the nice thing you can do is you could write this in a matrix equation, 0.7, getting the coefficients of each of those two, keeping the ordering consistent, V1, V2 in the order there. And this would be negative 0.5, 0.5, and written as a matrix equation, remember, these equations would be equivalent to this system where the right-hand side vector is just 6, 1. So this is a matrix equation representation of the two node voltage equations with two unknowns. And the idea is to solve for V1 and V2. And again, that can be done in a variety of ways. Can be done by hand, where you substitute V1, get an expression for V1 in terms of V2, and then substitute that into the other equation and then resolve V2 that way. Or plug it into any matrix solver from a calculator or MATLAB, Python, whatever. And you can show that in this case, V1 is 10.32 volts and V2 is 6.129 volts, okay, right? So you have more voltage going through this node than you do through that node, okay, which kind of makes sense. There's a lot more resistance over here. So again, how you determine that, you know, you should just apply, you can, like I said, you can use any matrix solver that's available. And in the appendix of the Xi books, there is a overview of using, you know, Gaussian elimination to solve linear systems. So this is called Gaussian elimination. And again, that was what you used in your linear algebra, undergraduate linear algebra class. That's required for pretty much all engineering majors. So we'll do, let's do one more example. Example 4 is to, again, write the node voltage equations, and we will write this in a way to get two linear equations, set it up for a matrix equation, and then show you what the solution is, all right? So again, notice the decision of where the nodes are. We know what the voltage is at that particular point of the circuit. It's 10 volts, right? So we're labeling these other two nodes for which we don't know the voltage at, right? So again, you have node 1 and node 2. Let's do KCL for node 1. And then we'll do KCL for node 2. And so if we look at node 1, we know there's going to be 3 components because we could represent 3 outgoing currents. So one of them could be from the node to the ground. That would give us V1 over 5 ohms. We could go to the left, which would be V1 minus, what, 10, right? Because that node, there's 10 volts there, divided by 2 ohms, plus, and then going to the right, V1 minus V2 over 10. And summing those has to be equal to 0, okay? The next equation we would get for node 2, let's go from the node to the ground again. That would give us V2 over 5. And let's go to the left, V2 minus V1 over 10. You can see almost the same term there, just the signs are flipped. And oops, that should have been V1 up there, correct? Yeah. And then finally, we're going up over the 10 ohms back to V1, so back to 10 ohms there. So 10 volts. So there's, again, 10 volts there at that node. So, so we should have V2 minus 10 through the 10 ohm resistance, right? Equals 0, okay? And again, simplifying this, collecting the terms, collect all the V1 terms, which there are 3 in the first one, and then a single V2 term. You clean that up, you should get a system that looks like this. You'll have 8/10 times V1 minus 0.1. Okay, that's the first equation, times V1 and 2, and you should get a 5, okay, on the right-hand side. You can see the 5 coming up because look at that, 2 divided into 10, that's gonna be -5, pulls over that side. This equation, you've got 3 terms involving the V2, so you have to collect all those terms, and that'll be 0.4. The single V1 term will be -10th. You can see that. You're going to have -1/10 there. And then the only right-hand side possible that's going to be left is this is going to give you a -1 there. So this here is 1. So you have to solve that matrix equation, 2 by 2 linear system. And again, if you do that, you would show that it's 6.774. And V2 equals 4.193, okay? So again, we're not rehashing linear algebra here. It's assuming that you would be able to solve these and again, you can, as far as homework goes, and even any quizzes on final exam, you are perfectly allowed to use any solver you want in terms of MATLAB, Octave, Python code, or calculators. Basically, I think it's called rough or reduced form or something like that. And you should be able to plug in the coefficients and plug in the right hand side, and then get the two unknowns that you need. So scientific calculators that have that linear solver function in there, it's perfectly fine to use. So where we're headed in the next section on supernodes is another ability to write KCL equations in a way of avoiding situations where we have voltage sources or even current sources getting in the way, so to speak. Okay, and of making it a little bit more complicated to come up with an easy KCL equation, because we were able, there was only one voltage source here, and it was very easy to include that in all of the KCL equations. And it's possible we could have situations where we have multiple ones, and again, we can try to simplify the unknowns that we need to solve for using a technique called supernodes, which we will cover in the next lecture.